Welcome to The Explainer. Today, we're unpacking the absolute foundation of modern technology. Seriously, we're going to see exactly how abstract mathematical logic is transformed into the optimized, physical, digital circuits that power our entire world. It's this incredible journey from pure theory to physical engineering. Okay, let's dive into this. So here is our masterclass blueprint for today. We're starting off with the rules of Boolean logic, then moving right into the physical logic gates, exploring real-world logic families, learning to minimize with K-maps, and finally wrapping up with design and verification. All right, Act 1, the rules of Boolean logic, which is our mathematical foundation. Before we can build any physical tech, we first have to understand the rules of the game. To build a circuit, you need a language, right? And that language is Boolean algebra. It operates on a strict set of axioms, basic theorems, and properties. And this brilliantly illustrates how these basic theorems and canonical formulas give us a highly structured way to make sense of incredibly complex logic. Without these foundational properties, digital logic would literally just be noise. Now, engineers absolutely obsess over reduction and minimization. It's kind of funny, actually. They treat complex Boolean functions like incredibly messy rooms that desperately need organizing. You start with something sprawling and chaotic, and you use algebraic equations to tidy it all up until it's perfectly, beautifully efficient. Moving right along to Section 2, the 7 logic gates, the physical building blocks. Okay, this is the exact moment where those abstract mathematical rules actually manifest as physical decision makers in a circuit. Now, what's really interesting about this is how simple the core list is. We're talking about exactly 7 gates: not, and, or, NAND, NOR, XOR, and XNOR. That's it. That is the whole shebang. Yet, this represents the entire physical arsenal we use to construct every single digital operation imaginable. From your smartphone to a supercomputer, it all relies on combinations of these 7 gates. Section 3. Real-world logic families, taking it to the physical realm. So these gates don't just exist in a vacuum. They belong to specific physical logic families, like TTL and CMOS, that dictate how they operate in reality. It's always a trade-off. One family might give you a massive advantage in sheer speed, while the other might boast incredibly low power consumption. Understanding these distinct advantages, the limitations, and the real-world suitability of these physical families, well, that's exactly what separates pure theory from actual functional engineering. Which brings us to Section 4, minimizing with K-maps, the engineer's secret weapon. In digital engineering, efficiency isn't just a nice little bonus. It is absolutely everything. So you might be wondering, why do we even need K-maps when we already have Boolean algebra? I mean, we just talked about reducing functions algebraically, right? Well, algebra is great, for sure, but it can be super tedious and heavily prone to human error once those expressions start getting massive. So the crucial point is this golden rule of design: build the simplified expression with the minimum number of components. We apply K-map minimization to visually and rapidly simplify these expressions because a minimized expression equals a minimized physical circuit. Fewer components literally mean the technology you're building is cheaper to manufacture, it's faster to operate, and it's smaller in physical size. It's a total game changer. Applying K-map minimization allows us to achieve the absolute optimum logic function. It takes those sprawling, messy algebraic equations we started with and funnels them into a highly optimized, elegant blueprint that's totally ready for manufacturing. Finally, we reach Section 5, design and verification, proving the circuit works. Let's move to and see how this builds into an actual engineering workflow. This is where we transition from having a brilliant design on paper to proving it will physically work. Step 1, we use our K-maps to simplify the expression. Step 2, we represent that expression using universal gates. Universal gates, like NAND and NOR, are basically the ultimate multi-tools of the circuit world because you can build any logic function using just them alone. And finally, Step 3, we verify the circuit's correctness using a truth table. The truth table is the ultimate judge here. It maps out every single possible input to prove beyond a shadow of a doubt that your output is flawlessly correct. You now completely understand the workflow from theoretical Boolean algebra all the way to proving circuit correctness. That verification step is incredibly powerful. So, here's the question I want to leave you with today. Now that you know how universal gates and K-maps build optimized circuits verified by truth tables, what complex decisions will you engineer next? Thank you so much for joining me for this explainer, and I really hope this empowers you to look at the digital world in a completely new, structured way.